In the black silence between stars, fragments of lost worlds drift unseen. They are older than Earth, older than the Sun, carrying within them the frozen chemistry of alien skies. Most pass without witness, but sometimes, chance allows one to be seen. On July 1st, 2025, the Atlas Survey telescope in Chile recorded a faint moving point of light. At first it seemed ordinary, just another comet or asteroid, yet its motion whispered otherwise. Calculations showed a hyperbolic path, a speed too great to be bound by the sun. Within hours, astronomers realized this was not local. It was a traveler from interstellar space, designated 3I Atlas. Only twice before had such visitors been found. Oumuamua in 2017, enigmatic and elongated. Borisov in 2019, a comet rich in dust and gas. Now came Atlas, different again, fragile, unstable, with chemistry unlike anything seen nearby. Its dust cocoon hinted at weakness, its glow at secrets from another star. For a brief season it will pass through the solar system, then vanish forever. In its light, humanity has been offered not just data, but a reminder that the galaxy is alive with travelers, and that even silence can carry a story across the dark. Welcome. You are watching Whisper Science. Make sure to subscribe and join us for more amazing science content. Now, let's move back to the video. On July 1st, 2025, a faint moving point of light appeared in the records of the Atlas Survey telescope in Chile. At first, it seemed unremarkable, just one more speck, drifting among countless stars. Yet almost immediately, astronomers noticed something unusual. The trajectory did not align with the familiar dance of objects bound to the sun. It whispered of an origin beyond. Within hours, alerts were sent, and telescopes worldwide turned their gaze. Archival images revealed it had been there weeks earlier, passing quietly, unnoticed among star-crowded fields. Piece by piece, the orbit was reconstructed, until the truth was undeniable. This was not a child of our solar system, but a messenger from the galactic beyond. Its hyperbolic path and its speed betrayed it as an interstellar wanderer. Memories of past visitors returned. In 2017, Oumuamua puzzled scientists with its elongated body and unexplained acceleration. In 2019, Borisov displayed a familiar cometary tail, rich in dust and gas. Now in 2025 came 3I Atlas, more fragile, more elusive. Its activity was faint, barely perceptible, a small coma, a hint of a tail stretching away into darkness. At discovery, it lay more than 4 astronomical units from the Sun, far beyond the orbit of Mars. Its light was weak, its motion across the sky subtle. Only the sensitive eyes of wide sky surveys could catch it, and even then, only through careful analysis of crowded star fields. To find it was to discover a whisper hidden in the cosmic noise. As its orbit became clear, so too did its fate. It would pass once through our neighborhood, then vanish into interstellar space, never to return. The eccentricity of its path, the high velocity relative to the Sun, all confirmed what astronomers had suspected. It was the third interstellar visitor known to humanity. Spectroscopic studies began quickly. Some telescopes caught glimpses of its coma, tinged with reddish hues. Subtle emissions hinted at water vapor and carbon-based compounds. In ultraviolet light, a more definite signal appeared. Hydroxyl radicals born from sublimating water, even at distances where solar heat is faint. The nucleus itself remained hidden, its size uncertain, its core masked by dust and ice. In those early days, the discovery carried more than scientific significance. It carried wonder. Another ancient traveler, born under alien suns, had revealed itself, however briefly. Humanity once again stood at the shoreline of the galactic ocean, watching a fragment from another world drift past. It was found almost by accident, but its arrival echoed through science and through imagination alike. Opens in silence, broken only by data streaming in from multiple space and ground-based observatories. The shock is not dramatic with explosions or alarms, but subtle, relentless. A series of anomalies stacking up until 3I Atlas refuses to fit any known pattern. It begins when the James Webb Space Telescope on August 6, 2025 turns its near-infrared spectrograph toward Atlas. Spectra emerge not with expected water vapor dominance, but with a coma dominated by carbon dioxide. The CO2 to H2O mixing ratio measures around 8:1, one of the highest ratios ever observed. In a comet at that distance from the Sun, water is present, but comparatively muted. Ice, dust, COOCs, all part of the picture, but the CO2 is emphatic. This finding confounds many assumptions about how comets act at large heliocentric distances and what their volatile inventories usually hold. Almost in parallel, Spherix imaging spectrophotometry confirms ice absorption features. Water ice grains are detected, but the gas emission map shows a vast, extended CO2 coma. The amount of CO2 outgassing, estimated, is enormous compared to that of water and carbon monoxide. Normally, comets become active when water begins sublimation closer in. But Atlas has started speaking in CO2 long before water takes a leading role. Another shock comes through polarimetric studies. The Very Large Telescope, Nordic Optical Telescope, Rogan Observatory have measured light-scattering properties of the coma. These show an extremely deep and narrow negative polarization branch, reaching a minimum of about -2.7% at small phase angles. The inversion angle where polarization flips sign is about 17 degrees. This behavior has no analog among known solar system comets or interstellar objects before. Dust grains, icy particles, organixol, seem arranged in ways unlike typical comets. Hubble imaging adds to the surprise. Its July 21st image of Atlas shows a teardrop-shaped cocoon of dust extending from the icy nucleus. But even Hubble cannot clearly resolve the solid core. Size estimates vary. The nucleus might be as large as 5.6 kilometers in diameter, or as small as a few hundred meters, depending on how much light comes from dust rather than ice. The uncertainty is wide enough to unsettle what was thought probable. Then the comet changes color. Whereas early observations described a reddish coma, heavier dust and organics dominating scattered light, Atlas begins to glow with greenish hue as it draws nearer, suggesting production of cyanide or other gases, icy grains becoming more efficient scatterers in sunlight. The shift is not gradual, but perceptible, abrupt enough to make astronomers pause. Orbital mechanics contributes its own surprise. Atlas moves on a hyperbolic path so unbound, so fast over 130,000 miles per hour relative to the Sun that it cannot be captured, cannot return. Its path is retrograde, inclined only slightly relative to the ecliptic plane. Rather than arriving from some random orientation above or below the solar system's disk, it comes nearly aligned with the plane of planets, though moving in the opposite direction. That conjunction is unlikely, bringing its origin and its journey into sharper mystery. Each individual surprise would be noteworthy. Together they assemble a portrait of 3I Atlas that resists categorization. Its high CO2 content, its distant activity, its unusual light scattering, its color change, its velocity and inclination all combine into scientific shock. Atlas does not behave like solar system comets. It does not behave like Borisov. It does not behave like anything seen before. In this moment, astronomy must confront the limits of its models, the gaps in assumptions. The shock is not in disaster, but in realignment. What was believed about comets, their chemistry, their birthplaces, their journeys, must expand. Within this shock, there is urgency. Observers must adjust, point their instruments, recalibrate expectations, because if even one interstellar visitor can surprise so much, then the universe may contain many more, each with their own secrets, waiting to overturn familiar notions. The initial shock surrounding the detection of 3I Atlas soon gave way to a phase of deeper inquiry. If the comet's chemistry and behavior challenged familiar expectations, then only a more precise investigation could untangle the mystery of its true nature. Astronomers, planetary scientists, and astrophysicists across continents shifted their focus. The object became not just a curiosity, but a test case, a rare opportunity to study a fragment of an alien planetary system before it slipped away forever. The first path of inquiry was dynamical. Using thousands of position measurements gathered by ground-based telescopes in July and August, orbital reconstruction began. Computer simulations traced its trajectory backward, far beyond the reach of the solar system. These integrations suggested that 3I Atlas had been wandering the galactic disk for billions of years. The kinematic analysis indicated a probable age of 3 to 11 billion years since its ejection from a parent system. That span encompasses epochs older than the Sun itself. It implies that 3I Atlas could have been launched during the early assembly of planets around a now distant star, preserved as a frozen shard long before Earth existed. The question of ejection mechanism drew interest. Most likely, gravitational scattering during the tumult of planetary formation flung this object out of its birth system. Giant planets, shifting orbits, chaotic encounters all could have sent comets into galactic exile. Over immense timescales, these orphaned fragments accumulate, filling the interstellar medium with icy bodies whose paths are rarely crossed by the sun. ATLAs happen to intersect Earth's sky only by chance. Its trajectory aligned with our survey instruments for a fleeting interval. As the orbit was refined, scientists sought to pinpoint a potential origin star. This proved elusive. Galactic dynamics blurred precise tracing. Nearby stellar associations were checked, but the uncertainties were too large. The comet's journey likely spanned multiple revolutions of the Milky Way, making its birthplace untraceable. What could be said with confidence was that it did not come from the Sun's own Oort cloud. Its speed relative to the Sun, over 55 kilometers per second, exceeded the velocity limits of solar system reservoirs. The object's unbound orbit made it clear it was interstellar. Once its trajectory was characterized, attention turned to composition. Spectroscopy, polarimetry, and photometry worked in tandem. The James Webb Space Telescope detected a coma dominated by carbon dioxide. This result alone was striking. In most solar comets, water is the principal volatile, with CO2 and CO playing supporting roles. Yet here was a visitor in which CO2, outgassing, eclipsed water by nearly an order of magnitude. Even at 4 astronomical units, water activity was already measurable through hydroxyl emissions. But carbon dioxide was the dominant breath of this comet. Such abundance pointed to a radically different chemical heritage, perhaps reflecting the conditions of its natal protoplanetary disk. The polarimetric anomalies added further intrigue. Observations from European observatories indicated light-scattering behaviors never before documented. Negative polarization of extraordinary depth suggested unusual grain structures, possibly fragile, porous aggregates with coatings of exotic ices. This hinted that the comet's surface layers had endured long exposure to cosmic rays, altering their chemistry in ways uncommon to comets in the solar system. The grain seemed to carry the scars of interstellar radiation environments. Ground-based observations revealed further complexities. The color of the coma evolved. Early frames showed reddish dust typical of organic-rich material. Later observations caught greenish hues, likely caused by emission of diatomic carbon and cyanogen gases. The transition between these color phases suggested layered volatiles within the nucleus, sublimating at different rates as solar heating intensified. These emissions confirmed that the comet was active, despite its great distance. Its volatile storehouse was not inert, but responsive, though fragile and short-lived. The morphology of the coma also raised questions. Rather than forming a neat, symmetric halo, it appeared elongated, asymmetrical, even ragged. Some images revealed faint striations and uneven jets, suggesting localized eruptions from beneath the surface. This pointed to a nucleus riddled with fractures, venting unevenly into space. The fragility of the structure seemed evident. Scientists speculated that as perihelion approached, the nucleus might not survive intact. The faint, teardrop-shaped cocoon of dust, recorded by Hubble, reinforced the idea of a body already breaking down under mild solar pressure. Another element of the investigation was the search for isotopic ratios. Though direct sampling was impossible, astronomers hoped to infer DH ratios of water through spectral lines. Preliminary hints suggested values, not inconsistent with solar system comets, but uncertainties remained high. If confirmed, such ratios could provide comparative evidence of how different stellar nurseries synthesize and preserve water ice. A detection of anomalous values could hint at unique conditions in ATLAS's parent system. For now, the question lingered unresolved. The comet's photometric variability also drew notice. Measurements showed irregular brightness fluctuations over timescales of hours to days. This variability could reflect rotation of the nucleus, exposing active regions intermittently. Estimates of rotation period ranged from several hours to a full day, though the data remained noisy. Whatever the exact period, it was clear that the comet's surface was dynamic. This dynamism offered clues to the structure of the nucleus, perhaps irregular in shape, perhaps fractured, tumbling as it crossed the void. To place Atlas in context, comparisons with Oumuamua and Borisov were inevitable. Oumuamua displayed no coma, only an enigmatic, non-gravitational acceleration. Borisov looked much like a typical comet, with clear water and dust activity. Atlas straddled the line between the two, active, but in unexpected ways, fragile, but carrying unusual chemistry. It represented a new archetype of interstellar object, different from its predecessors. Its uniqueness reminded scientists that 3 detections are not enough to define a population. Each object may be distinct, shaped by different stellar environments, by different histories of radiation, collisions, and exile. The deeper investigation also touched philosophical chords. If Atlas was as old as models suggest, then it had traveled through the galaxy since before our planet had an atmosphere. It had orbited the Milky Way multiple times, passing through spiral arms, brushing past supernova shock fronts, absorbing radiation from stars that have long since died. In its ice may be preserved isotopes from ancient stellar nucleosynthesis events, chemical signatures that predate the Sun. To study it is to touch a fossil of galactic history, frozen and drifting for untold ages. Observational campaigns intensified. The Vera Rubin Observatory, scheduled to begin full survey operations soon, was enlisted to track faint variations. JWST scheduled multiple windows. European Southern Observatory telescopes captured polarimetric sequences. Each dataset added a new thread to the tapestry, but the picture remained incomplete. Astronomers faced a race against time. Atlas was inbound, brightening slowly, but it would soon recede. Its closest passage would come and go within months. After that, it would fade irretrievably into the black. The investigative focus also turned practical. Could future missions ever be prepared to intercept such objects? ESA's Comet Interceptor mission, designed to wait at the Earth-Sun L2 point, was mentioned as a pathfinder. If Atlas had been discovered earlier, such a mission could have been diverted to encounter it. But discovery came too late. The comet would pass unvisited, its secrets gleaned only from afar. Scientists began to argue that the time had come to establish a standing fleet of rapid response missions, ready to launch at the first detection of an interstellar visitor. Without such readiness, opportunities would always be lost. Through all of this investigation, one feeling remained constant. The comet was fragile, fragmented, uncertain in its revelations, but it was undeniably alien. Its chemistry, its dust, its trajectory all whispered of another place, another time. The deeper astronomers probed, the more questions emerged. Atlas seemed to resist closure, offering evidence that hinted at answers, but never fully revealed them. It was not just a scientific challenge, but a reminder of cosmic humility. Deeper investigation into 3I Atlas brought no simple clarity. Instead, it revealed complexity layered upon complexity, each observation opening new mysteries. Its orbit tied it to ancient galactic history. Its volatiles defied local norms. Its dust grains told of radiation unknown in our system. Its morphology suggested fragility and impermanence. Each fact deepened the enigma. In chasing those facts, humanity found itself again confronting the enormity of the galaxy and the strangeness of the objects that drift between stars. The early investigations of 3I ATLAs revealed it to be a visitor unlike any before. But as weeks passed and data accumulated, the mystery only deepened. It was no longer enough to call it a comet with unusual chemistry. Each new observation suggested layers of strangeness, as though the object itself resisted comprehension. What began as a faint discovery had grown into a challenge to our understanding of how planetary systems create and lose their icy fragments. One of the most disquieting features was the way the comet's activity evolved. In August, its coma was described as fragile, but consistent. By September, astronomers noted erratic jets, asymmetrical emissions, and a cocoon of dust that did not behave like that of ordinary comets. The coma appeared distorted, as though structural weakness inside the nucleus was forcing material outward in irregular bursts. Some observers likened it to a body unraveling, a snowball disintegrating under sunlight, after billions of years of survival in darkness. This instability raised the prospect that Atlas might not survive its solar passage intact. Theoretical models showed that even moderate heating could trigger complete fragmentation, reducing the nucleus to a field of dust and gas. If that occurred, humanity's view of the comet would vanish into a diffuse cloud. The possibility created urgency. Instruments had to gather as much information as possible before the object collapsed. In this sense, Atlas was not just mysterious, but fragile, a story that might be erased before its final lines could be read. The polarimetric anomalies added to the unease. Light scattering at small angles indicated dust unlike any catalogued before. The negative polarization branch was far deeper than known comets, suggesting grains that were either extraordinarily porous or coated with exotic ices. These properties hinted at prolonged exposure to interstellar radiation fields, altering the microstructure of surface layers. If so, the comet carried not just a record of its birth environment, but of countless ages drifting between stars, scarred by cosmic rays, frozen in interstellar silence. Astronomers debated what this meant for planetary science. If Atlas represented even a small fraction of interstellar objects, then the diversity of materials scattered between stars was far greater than anticipated. Oumuamua had looked inert. Borisov had resembled a typical comet. But Atlas seemed unstable, chemically distinct, and on the brink of self-destruction. Were these three objects simply rare extremes, or were they glimpses of an unseen galactic population far richer than imagined? The escalation was not only scientific, but philosophical. Each detection of an interstellar visitor carried with it an implied question. How many of these bodies roam unseen in the vastness between stars? The discovery of 3 within a single decade suggested a galaxy teeming with exiled fragments. If so, then Earth and its neighboring planets are not isolated worlds, but islands along a cosmic trade route of drifting relics. Each one could contain chemistry alien to the solar system, carrying memories of stars long gone. Detection difficulty reinforced the sense of scale. Atlas was faint, nearly invisible against the star-crowded sky. Its discovery was almost accidental. How many similar objects passed within a few astronomical units, unseen, unrecorded, vanishing back into the dark? Sky surveys like Atlas and Pan-STARRS had widened humanity's vision, but their sensitivity was limited. Only with future observatories like the Vera Rubin Observatory would the true frequency of interstellar visitors be revealed. The mystery deepened not only because of what was seen, but because of what surely went unseen. The comet's kinematic story escalated the enigma further. Its orbital analysis suggested an age of billions of years. It had likely circled the galaxy multiple times, moving through spiral arms, exposed to varying stellar densities, passing near stars and nebulae. Each passage could have altered its surface, layering it with scars invisible to the eye, but detectable in its scattering properties. The comet was not merely an object from another system. It was a relic of galactic history, older than the Sun, shaped by forces spanning eons. Its retrograde path relative to the solar system added another twist. Moving against the planetary direction, Atlas threaded itself through the solar plane in opposition. Such a path was improbable and unlikely to be repeated. It heightened the sense that this was a once-in-a-lifetime observation, a chance alignment that would never occur again. The mystery deepened not because the object withheld answers, but because its very presence demanded new questions about probability, origin, and destiny. Speculative models began to circulate. Perhaps Atlas was not a conventional comet, but the fragment of a disrupted planetesimal. Its fragility, its chemical signature, its instability could all be explained if it had been fractured by early planetary collisions, then ejected into interstellar space. Others suggested it was part of a primordial population formed under unusual conditions in ancient protoplanetary disks. Its high CO2 ratio could reflect environments rich in volatile carbon compounds, environments uncommon around sun-like stars. Still others argued that Atlas might be representative of bodies formed near the snowlines of giant exoplanetary systems, preserved under cold, carbon dioxide-dominated conditions. The deeper the investigation went, the more elusive the answers became. For every hypothesis, data presented contradictions. For every attempt at classification, ATLA slipped free of categories. In that sense, the mystery was not only about the object itself, but about the nature of science confronted with rarity. With only 3 interstellar objects ever observed, no population baseline exists. Atlas magnified that limitation, reminding astronomers that the universe often reveals its diversity, not gradually, but through startling exceptions. As the comet brightened in late August, ground-based observers captured longer exposure images. The coma expanded, glowing green with diatomic carbon emissions, but the nucleus remained shrouded. The inability to see the solid core directly reinforced its ghostly character. It was a presence that could be measured, analyzed, debated, but never touched. Its fragility and its unbound path meant that it would leave without trace, a mystery deepened by the certainty of its disappearance. The escalation also carried emotional weight. Scientists watching the object knew they were witnessing something rare, fragile, and fleeting. The comet was a reminder of how temporary encounters shape human knowledge. It would cross the solar system only once, visible for a short span of months. Then it would vanish forever, carrying its secrets back into interstellar night. That sense of impermanence intensified the mystery. It was not only that Atlas was difficult to understand, but that time itself conspired against full comprehension. In the laboratories of theory, computer models sought to simulate its behavior. Dust particle simulations, volatile sublimation models, structural integrity tests all tried to explain the observed instabilities. None were complete. Some suggested internal layering of ices, others proposed cavities collapsing as heating reached deeper strata. Each model illuminated part of the truth, but left shadows elsewhere. The comet remained beyond full grasp, like a whisper carried on galactic winds. As September waned, the object's story had escalated into something larger than one comet. It became a symbol of the unknown interstellar population, a representative of all the drifting bodies humanity might never see. Its strangeness reminded astronomers that the Milky Way is a dynamic ecosystem, filled with fragments born of distant worlds, cast out to wander. Each one may hold clues to chemistry, history, even the origins of life. But each one may also slip away before answers can be found. When an object resists clear classification, speculation inevitably fills the void. For 3I Atlas, the flood of theories was as vast as the interstellar space it had crossed. Each observation carried within it the seeds of possible explanation, but none alone could resolve the riddle. Instead, astronomers were left with a constellation of possibilities, each demanding attention, each pointing toward different visions of cosmic origin. One of the earliest theories proposed that Atlas is a survivor of planetary birth violence. In young planetary systems, giant planets migrate and collide, scattering debris outward. Comets, asteroids, and planetesimals can be ejected with such velocity that they never return, condemned to drift the galaxy indefinitely. Atlas may be one of these shards. Its high carbon dioxide levels could reflect a nursery rich in volatile ices, perhaps colder and chemically distinct from the region where Earth was formed. If so, its present fragility is a consequence of both ancient violence and unending exile. Another line of speculation focused on the chemical ratios themselves. Why would carbon dioxide dominate so strongly over water? Some models suggest a disk region around its parent star, where carbon dioxide ice was more stable than water ice. A snow line shifted inward by stellar luminosity or by local chemistry. Others suggest prolonged cosmic ray bombardment altered water into secondary compounds, leaving CO2 as the more persistent, volatile. If this is true, then Atlas is less a comet than a chemical fossil, preserving in its balance of gases the peculiarities of a planetary system long vanished. There were also ideas that Atlas might be a fragment of a larger body. Its instability, its coma shape, its apparent weakness suggested it could be the shattered remnant of a planetesimal, once hundreds of kilometers wide. Over billions of years, collisions and tidal disruptions may have ground it down. What arrived at the solar system was not a whole comet, but the broken bone of a much larger structure. This view would explain why its light-scattering properties seem unusual fragments of porous rubble. Fragile lattice of dust and ice, no longer compact, but airy and weak. Theories of panspermia surfaced as they always do when alien objects appear. Could Atlas have carried organic precursors through interstellar space? Could such travelers be responsible for seeding young worlds with the building blocks of life? The detection of organics in Borisov and in many solar comets made the speculation credible, though unproven. If carbon-bearing molecules exist within Atlas, they could have traveled billions of years unaltered, offering evidence that life's chemistry is not unique to one star system, but widespread across the galaxy. This speculation did not claim certainty, but raised profound possibility. Some scientists wondered if Atlas might hint at populations of comets that formed around exotic stars. Around red dwarfs, with their cooler disks, CO2 might condense readily, while water remains vaporized. Around massive stars with short lifespans, chemistry may freeze differently, leaving imprints now visible in a survivor like Atlas, if true. Then each interstellar visitor is not random, but a sample return mission from alien planetary nurseries. Collectively, they form a galactic survey written in ice. The speculation reached even further in imagination. A minority entertained the possibility of artificial origin, though most treated it cautiously. Oumuamua had provoked similar whispers, because of its acceleration and unusual shape. Atlas seemed more clearly cometary, but its instability and its unusual chemistry sparked faint echoes of that debate. Could such objects be the wreckage of engineered structures, long since degraded into dust and ice? Most dismissed this as unlikely, but the mere fact that the question was raised shows the depth of the mystery. Another strand of thought was that interstellar objects might serve as natural messengers. Their trajectories intersect many systems across billions of years. They may carry chemistry from one stellar nursery to another, binding the galaxy into a web of exchange. In this view, Atlas is part of a cosmic circulation system. Just as rivers carry sediments across continents, comets may carry atoms and molecules across stellar neighborhoods. What humanity witnessed was not just a single comet, but a node in a galactic process of distribution and renewal. Philosophers of science noted that 3 interstellar visitors are too few for any firm conclusions. Oumuamua, Borisov, and Atlas may not represent categories, but singularities, each unique, each unrepeatable. Yet the speculation that flows from them is valuable. It forces models of planetary formation to account for greater diversity. It compels chemistry to adapt to ratios not seen locally. It expands the horizon of possibility for what kinds of objects may exist in the Milky Way. Underlying all speculation was the awareness of time. Atlas may have been traveling since before the Sun formed. It may have orbited the galaxy dozens of times, each pass through spiral arms, altering its surface. If its chemistry is unusual, perhaps it is because cosmic rays have modified its ices over eons. If its dust is fragile, perhaps repeated microcollisions have hollowed its grains. Every speculation must account not only for formation, but for the incomprehensible duration of interstellar drift. As data accumulated, speculation began to refine into testable questions. If the comet is indeed carbon dioxide rich because of formation zone, then isotopic signatures should reflect that. If it is fragmentary, then its brightness variability should reveal tumbling rotation and uneven mass. If it carries exotic organics, spectroscopy at particular wavelengths should confirm them. Each speculation became a guide for observation, pointing telescopes toward what to look for next. In the end, the speculation surrounding ATLAs was not a weakness of science, but its strength. To imagine possibilities is to prepare for discovery, to ask whether this comet is a shard of a larger world, a chemical fossil of an alien disk, a seed of organic compounds, or simply a fragile wanderer shaped by time, is to push understanding outward. Atlas inspired not one story, but many, each plausible, each waiting for evidence. And perhaps this is the deepest truth about interstellar visitors. They do not only bring chemistry and dust, they bring mystery itself. Each one invites humanity to speculate not only about what they are, but about what the galaxy is. They remind us that beyond the familiar borders of the solar system lies a sea of fragments, each with its own tale, each a speculation waiting to be transformed into knowledge. The mystery of 3I Atlas deepened not by closing doors, but by opening new ones. The object resisted classification, challenged expectations, and forced questions about galactic abundance, planetary processes, and cosmic timescales. Its instability and its fragility underscored the urgency of study. Its unique chemistry defied comparison. Its improbable path emphasized the rarity of encounter. In every way, ATLA seemed designed to remind humanity that the universe is more complex than any model, more abundant in surprises than any expectation. And so, as the comet moved closer to the sun, the mystery grew. Each image, each spectrum, each calculation did not resolve the puzzle, but added depth to it. Atlas had escalated into a phenomenon larger than itself. It was not just a comet. It was a question, a challenge, a fragment of galactic memory pressing itself briefly into human awareness. And when it left, the mystery would remain, deepened and unresolved. The discovery of 3I Atlas not only expanded knowledge of interstellar objects, it also exposed the fragility of human readiness to study them. Each glimpse of a traveler from beyond is brief, fleeting, and often accidental. The comet will never return. Its secrets can only be caught in the narrow window of its solar passage. This reality places immense weight on the tools of observation, the instruments poised across Earth and space, and the readiness of science to seize the moment. At the front lines of discovery stand the wide-field surveys. The Atlas telescope itself, with its modest mirrors but vast sky coverage, first captured Atlas against the crowded stars of June and July. Such surveys are the eyes that sweep the heavens nightly, recording millions of faint points of light, then sifting them for motion. Yet as powerful as they are, they remain limited by sensitivity and weather. The Vera Rubin Observatory, now completing its commissioning phase, is expected to change that balance. With its enormous field of view and rapid cadence, Rubin will map the sky in detail never before attempted. Models suggest it may detect dozens of interstellar visitors over a decade, turning rare accidents into a steady stream of discoveries. Once detection occurs, the second wave of tools comes into play. Large ground-based telescopes like the Very Large Telescope in Chile, Gemini in Hawaii, and Keck on Mauna Kea provide the spectroscopic power to analyze faint emissions. They tease out lines of hydroxyl, cyanide, diatomic carbon, and carbon dioxide, building the chemical portrait of the object. In the case of ATLAs, polarimetric observations revealed dust-scattering properties that shocked expectations, pointing to fragile interstellar grains altered by cosmic radiation. Without such facilities, the comet would remain only a dot of light with an unusual orbit. With them, it becomes a laboratory of alien chemistry. Space-based telescopes extend that laboratory into regions unreachable from the ground. The Hubble Space Telescope, even in its fourth decade, provided high-resolution images of ATLAS's coma, showing the teardrop-shaped dust cocoon and placing constraints on nucleus size. The James Webb Space Telescope brought its infrared spectrographs to bear, revealing that the coma was dominated by carbon dioxide rather than water. This result reshaped theories about the comet's origin, suggesting formation in an environment colder or chemically distinct from the sun's nursery. These instruments orbiting above the atmosphere transform faint whispers of light into scientific data, recording signatures invisible from Earth's surface. Behind these telescopes lies a network of coordination. The Minor Planet Center receives alerts, consolidates measurements, and calculates orbits within hours. Automated software fits trajectories, determines whether they are bound or unbound, and flags anomalies. This system is the nervous system of interstellar research, allowing astronomers worldwide to pivot quickly. Without it, an object like Atlas could pass unnoticed until it was already too far to study. The scientific community also looks beyond passive observation. The European Space Agency's Comet Interceptor mission represents a new strategy. Instead of waiting for a known target, it sits in readiness at the Sun-Earth L2 point. Its purpose is to intercept a comet discovered inbound, perhaps even an interstellar one, like a TLAS. With multiple flyby probes, it can capture close-range data that telescopes cannot. Had Atlas been found earlier, Comet Interceptor might have been a candidate. Its very existence is a response to the lessons of Oumuamua, Borisov, and now ATLAS. It reflects recognition that the galaxy will send such visitors again, and that readiness must exist when chance provides the opportunity. The tools extend further into the theoretical. High-powered simulations run on supercomputers, trace orbital histories, model sublimation processes, and reconstruct chemical evolution under cosmic rays. For ATLA's models tested whether its high carbon dioxide levels arose from initial formation chemistry or from long-term irradiation. Other models examined its structural weakness, exploring whether layered ices or internal cavities could explain its instability. These computational tools are as vital as telescopes, for they allow hypotheses to be tested against the fragmentary data returned. New instruments are being prepared with interstellar visitors in mind. Spherix, scheduled for launch soon, will survey the sky in near-infrared, cataloging spectral signatures of ices and dust. Its mission is not to target one comet, but to build a vast library of cosmic chemistry. Yet, if another interstellar body appears, Spherix may provide invaluable comparative data. Likewise, future radio telescopes may detect neutral gas emissions, broadening the toolkit available. Ongoing testing of theories requires patience as well as innovation. Astronomers must compare Atlas not only to Borisov and Oumuamua, but to hundreds of ordinary solar comets. Only by cataloging similarities and differences can patterns emerge. Already the unusually high CO2 content of Atlas stands apart from most solar comets, suggesting either a unique origin or a type of body not represented in local reservoirs. Testing such conclusions demands years of accumulated comparisons, each observation a pixel in a broader picture. Perhaps the greatest tool in this process is not a single telescope or mission, but coordination itself. International consortia, data-sharing protocols, and rapid alert systems turn a discovery into a global enterprise. Within days of ATLAS's detection, observatories from Europe, Asia, the Americas, and space-coordinated efforts, this network ensures that when a fragile visitor passes, humanity's collective eye is focused, gathering all it can before the opportunity fades. The case of ATLA demonstrates that readiness remains imperfect. The comet was discovered only weeks before detailed observation began. No mission could be launched to intercept it. Much of its nucleus remains hidden, unresolved by even the best telescopes. In many ways, Atlas is a reminder of what is lost as much as what is gained. But it also galvanizes preparation. Each interstellar visitor strengthens the case for faster surveys, for standby missions, for broader networks. Science builds its arsenal not only from what it learns, but from what it misses. Instruments can dissect spectra, measure polarization, trace orbits, and simulate behavior. But the comet itself will move on, vanishing into interstellar night. The lesson of ongoing testing is therefore not only to study what is present, but to prepare for what is next. Tools sharpened by Atlas will be ready for the next messenger, and the one after that. In this way, interstellar visitors are both subjects and catalysts, objects of study and engines of progress. The story of 3i Atlas is thus inseparable from the story of the tools that pursued it. Each lens, mirror, detector, and processor became a bridge between humanity and an object born of another star. Each one carried the weight of fleeting opportunity. Together they formed a chorus, turning faint photons into knowledge, knowledge into questions, and questions into readiness. The comet may be temporary, but the tools endure, waiting for the next whisper from the galactic deep. The story of 3i Atlas cannot end with numbers alone. Beyond orbital diagrams, chemical ratios, and brightness curves, there lies the deeper resonance of what this comet represents. For in its fragile passage, humanity glimpsed more than a body of ice and dust. It glimpsed the scale of time, the immensity of the galaxy, and the humility of fleeting encounters with the unknown. Atlas is older than the Earth. The models that trace its orbit backward through galactic tides suggest that it was cast out billions of years ago. Perhaps it was ejected as planets formed around a young star long since extinguished. Perhaps it circled the galaxy while the first multicellular life was only beginning to appear on Earth. In its ice may be preserved traces of ancient stellar environments, isotopes formed in supernova long before the sun ignited. To look upon it is to look upon a relic of epochs before human history, before planetary history, before the very age of our solar system. The comet's fragility speaks of impermanence. Its dust cocoon, its uneven jets, its risk of disintegration, all remind that survival across billions of years does not guarantee survival in the present. In this way, ATLAS becomes a metaphor for existence itself. Time preserves, But time also erodes. What endures through ages can dissolve in a moment under the light of a nearby star. The universe is not a museum where relics remain pristine. It is a living ocean of change, where even the oldest travelers break apart when conditions shift. Observing Atlas also reshaped how humanity views its place in the galaxy. For centuries, comets were thought to be omens within the solar system. Only recently has science recognized that comets may be universal, born in the disks of countless stars. Interstellar objects like ATLAS prove this truth. They show that planetary systems do not remain sealed within themselves. They shed fragments into interstellar space, fragments that can cross vast distances and reach alien suns. The solar system is not isolated. It is part of a galactic web of exchange, linked invisibly to stars we cannot name. The philosophical echo of this realization is profound. If fragments of alien systems drift into ours, then fragments of ours drift into others. Across billions of years, countless shards of ice and rock have crossed the galaxy. Some may carry organics. Some may carry chemistry that, when falling onto a young world, becomes part of its story. In this way, the Milky Way may not be a collection of isolated star systems, but a community bound by drifting messengers. Each comet is a letter carried by cosmic winds, unreadable perhaps, but undeniably present. The presence of Atlas also sharpens the sense of human limitation. 3 interstellar visitors in less than a decade suggest that the galaxy is filled with them. Yet only now, with wide surveys and sensitive telescopes, has humanity begun to notice. How many passed unseen in centuries past? How many cross silently each year, without a single eye to record them? The awareness of this blindness is humbling. It shows that even as technology advances, the universe is far richer and more dynamic than perception allows. Atlas is a reminder not of what is known, but of what remains hidden. The comet's silence speaks as loudly as its data. It carries no message in language, no inscription in stone. Its whisper is light and dust. Yet the act of observing transforms that silence into meaning. Astronomers measured its eccentricity, its speed, its spectrum, and from those numbers built narratives of origin and journey. In doing so, they turned a mute fragment into a storyteller. The philosophy of science rests on this act: to listen where there are no words, to imagine where there are only faint traces, to find meaning in what would otherwise remain void. The emotional weight of ATLAS's passage cannot be dismissed. Scientists, students, and amateurs alike watched it through telescopes, knowing that it would never return. Its trajectory ensures that once it leaves the solar system, it will be gone forever, vanishing into interstellar night. The brief window of visibility becomes symbolic of life itself, transient and unrepeatable. To see it is to confront mortality on a cosmic scale. Even a traveler that endures billions of years can still fade into dust before human eyes. Figures such as Einstein and Hawking often reflected on the relationship between human knowledge and cosmic vastness. Einstein spoke of the mysterious as the most beautiful experience, the source of true art and science. Hawking reminded that humanity is just an advanced breed of primates on a minor planet of a very average star, yet capable of understanding the universe. ATLAS embodies these reflections. It is both mystery and revelation, both humbling and elevating. Its very strangeness becomes an invitation to wonder. In the end, Atlas leaves behind not definitive answers, but resonances. It has shown that interstellar objects are diverse, fragile, and ancient. It has suggested that the galaxy is populated with countless fragments, each a survivor of distant planetary histories. It has revealed that science must be ready, with tools and missions prepared for the next encounter. And beyond the science, it has reminded humanity of fragility, impermanence, and the immensity of time. The comet continues on its path now, outbound, fading. Soon it will be beyond the reach of telescopes. Its dust will disperse, its light will diminish, and it will vanish into the silence from which it came. Yet in the memory of its brief passage, humanity holds something enduring. It is the awareness that the universe is alive with travelers, that the solar system is not isolated, and that even in a single fleeting encounter, the cosmos can whisper truths older than the Earth. So the story closes as it began, in silence. A fragment of another world has crossed the stage of the solar system, fragile, temporary, and gone. What remains is awe, humility, and the recognition that mystery itself is a gift. Atlas departs, but the questions it leaves behind will endure for as long as humanity looks up, waiting for the next whisper from the galactic deep.